Okay, welcome to another exciting Java class. I don't know if you saw the email, but next week I will be on travel, or as some would say, out of station. I will do a makeup class, but the makeup class will be on a Sunday morning. I know Sunday morning class is a bummer, but it's only once, and so we will not make a habit of it. So what I have done is I have already uploaded an assignment, which I'm calling Homework 3 for no particular reason, and it's about Chapter 3. And so one of the things that I thought would make sense for us to do is to go over Chapter 3, unless there are some questions about Chapter 2. No, any questions about Chapter 2 or the homework that was due last night? No concerns? No questions? Okay, so then in Chapter 3, what I have done is I've created a series of assignments that have to do with things like the truth table. Only we're going to automate the discovery of the truth table. Who here doesn't know what a truth table is? Be honest. Oh, we've got a couple. Okay, so since everyone else here is such a genius, maybe you could explain what a truth table is. Would someone like to explain what a truth table is? Well, only one person admitted that they don't know it, and everybody else wouldn't admit it. So since that means, obviously, that you all know what it is, someone should be able to explain it.
Truth table is a logical representation of gates generally.
Well, a truth table is a logical representation of gates. Is sort of true, but also maybe not. Yeah, we don't need gates to do a truth table. Yes? Instructions? Logical representation of an instruction. That's interesting. Okay, well, I suppose in the broadest of sense that might be true. If I were going to describe a truth table, I would say it is a series of outputs given a series of inputs. It is a simple mapping between input to output. Come on in. The input is uniquely going to define the output. For any given input, we will know the output in a truth table using what's known as combinational logic. However, given the output, we may not necessarily know the input.
Yes.
So what we have is not what you might call an isomorphic mapping. It is not one-to-one. That is, I cannot go from every output to every input, but I can go from every input to every output. So it's a one-way mapping. So what we have is a way to represent a discrete function. That's what a truth table is. And because the number of states that are represented in the truth table is finite, I can say that the number of inputs must be finite, and the number of outputs is also finite. However, the number of truth tables that I can represent is literally infinite. So this is very interesting. Truth table has now been characterized as a discrete set, which maps an input into an output. That's essentially a truth table. So then the question is, do we need gates for this? And the answer is no, but you can implement it with gates. Do we need Boolean algebra for this? The answer is no, but you can implement it with Boolean algebra. Can you take any truth table and represent it with Boolean algebra? And the answer is yes, you can. Can you take any Boolean algebra and represent it with a truth table? And the answer is yes, you can. So from a Boolean algebraic statement, I can derive a truth table. And from a truth table, I can derive a Boolean algebraic statement. But there's more, right? Truth tables are so valuable because any truth table can be implemented in a minimum number of gate delays. And we like to say all truth tables can be implemented in 3 gate delays, provided you are willing to bear the cost, which means many gates. Moreover, it is the case that you can have multiple outputs, right? Multiple bits on output and multiple bits on input. You know, often we see truth tables with only a single bit worth of output. But in fact, you could have many bits on output. You could even have more bits on output than you have on input. And that's relatively easy to see, right? I could say, okay, given a 1, I will output 1, 1, 1, 1, 1. Given a 0, I will output 0, 0, 0, 0, 0. So it's easy to see how a single bit on input can give me multiple bits on output. Relatively easy, right? Suppose I said to you that, and we have this here in the back of the book, it's a question that's already been formulated for you to do for your homework. So suppose I said, given a truth table which has not been filled in, derive a program which automatically generates the output of the truth table. Come on in. So as it happens, it would be a relatively easy matter for me to fill out the truth table by inspection. But of course, that would avoid the goal of the exercise, which is to write a program that does the truth table for you, which is a far more interesting problem. In other words, we're trying to automate the filling in of the truth table. So I think if we have a computer that can do this for us, we're much better off. So let's see if we can run a few Boolean algebraic exercises with truth tables. Now, when we look at operators in Java, there are 2 kinds of, I'll call them Boolean algebraic operators. One deals only with true and false. And this is what we normally associate with in the set of all Boolean literals. A Boolean literal consists of either 0 or 1, or true and false. And if you think about it, in the set of all possible elements, that's it. That's all you get. And if you have Boolean algebraic formulas that input elements in that set, the output will be elements in that set. This is a very compelling thing, even though it's a very simple statement, and it has a very fancy name. We say that the algebra is closed under the Boolean algebraic operations. That is to say, under the operations of and, or, and not, the Boolean algebraic set will always output 0 or 1, and we will never leave that set. Think about the idea of square root, right? If you take the square root of a positive number, it is positive, and it is a real number. So real numbers come in, and real numbers come out. But if you take the square root of a negative number, it's imaginary, huh? So with an imaginary number, you are not closed under the real number set, under the operation of square root. You have left the set. So we can say that under the operation of multiplication, the set of real numbers is closed. Under the operation of addition, the set of real numbers is closed. But under the operation of square root, the set of real numbers is not closed, because we can go out of the real number set and into the imaginary set. No such operation exists for the Boolean algebra, because for all Boolean algebraic operations, the set is closed. Right? That means we will always get Boolean algebra to operate under a set of false and true elements, and the output will always be false and true, or sets of false and true. So now I'm looking at this truth table, which is on figure 3.8-1, page 30. And I trust everybody has a copy of the book, whether it be electronic or on paper. And so what I would do in the case like this is I would look at this large table, and then I see this Boolean algebraic expression, and I say, aha! There are 2 kinds of Boolean algebraic operators available to me in Java. One which operates on the Boolean literals, true and false, and the other which operates on underlying binary quantities. Underlying binary quantities refer to scalar values. These are the numeric quantities which are non-floating point values. So, for example, byte, that's 8 bits. Short, which is 16 bits. Char, which is unsigned 16 bits. Int, which is 32 bits signed. Or long, which is, hello, come on in, 64 bits signed. So when we think about these Boolean algebraic quantities, we're not thinking about scalar quantities. Boolean algebraic quantities are true and false. The bitwise vector represented by a 32-bit int consists of 32 ones and zeros. And those 32 ones and zeros can also be operated on. And so therein lies the source of another set of operations known as the bitwise vector operations of Java. You have these operations in C, you have the operations in C#, and you have the operations in C++. They're the same notation, the same operators. And so what you can do is you can do a series of exercises which allow you to experiment with these kinds of operations. Here's a let's do one from scratch. I don't like to use existing examples, so we'll write a new one just for fun. I'll call this the negative example. Okay. In the negative example, public static void main control J enter, I can get a printout of the underlying quantities for a given input element. Let's try something. We'll start off with an integer, which I will call x, and set it equal to a number. But I would like to represent the underlying bits of that number in a way that makes sense to me as a digital designer. And so instead of writing out a number in what some people call base 10, what other people call radix 10, or what is commonly called decimal, right? We know the name decimal. I would like to input the underlying binary in an efficient and compact form. And so what I will do is I will encode a hexadecimal literal into the quantity which we are now calling x. Let's give this a name, 0x, which represents a hexadecimal literal. And then if you think about hexadecimal, it's base 16. Base 16 means 16 symbols. The 16 symbols, starting at 0, which counts as one of the symbols, terminates, come on in, at F. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So with A, B, C, D, E, F, you can spell words. For example, dead. So now X is dead. That actually has a value, right? We can print out that value in decimal. S out, Control J, enter, and now we'll just print out X. And now this will give us a quantity. It will not print dead. It will print something else, right? What would it print, do you suppose? Well, there are a few different ways you can determine that in advance of running the program. If you would like to encode the hexadecimal numbers after 9, A, B, C, C, D, E, F, they are single symbols that represent decimal numbers 10, 11, 12, 13, 14, and 15. So those are decimal quantities. So if you would like to represent in decimal the symbolic number DEAD, base 16, what you would do is you would take D, whose decimal value is equal to 13, and we can make this a little bit nicer so that you can see it. A B, C, D, E, and F. There. So now it's clear. D corresponds with 13. So when we think about dead as a decimal quantity, we can rewrite it in what's known as positional notation. And so what that says is it's really equal to 13 times 16, which is the radix or base, raised to the 0, 1, 2, 3 power, plus. And now the next one is E. E corresponds to 14. I think you can see that there. So 14 times 16 raised to the 2 plus DEA, which is 10, times 16 raised to the 1 plus the last D in dead, which is 13 times 16 raised to the 0. 16 to the 0 is equal to 1, so it's really just 13. Or you could write it out if you like, 16 to the 0. So this is the positional notation, which should allow us to perform a computation. In fact, if we like, we can use the computer for this. We can say something on the order of, well, actually, I think we have calculators for this, don't we? Isn't there a calculator in this thing? Yeah, there's one. Calculators. So does this thing have power? That is to say, a power function? Because I would like 13 times 16 to the 3. So what do we got? 13 times 16. Now there should be a way to raise it to the 3. And now it says equals. Does that sound like too big a number? Plus 14 times 16 to the 2 equals plus 10 times 16 to the 1. How about we just write 160? Plus, and then it says at the end 13. And it gives me a number, 57,005. So let's see if that is correct. I hope I didn't make a mistake. 57,005. Thank George Boole. So this is a time when I usually tell the story about George Boole. Does everybody know who George Boole was? There is a term in English called an eponym. An eponym is a term which is named after a person. For example, Einsteinian notation is named after Einstein. Boolean algebra is named after George Boole. George Boole, who lived in the late 1800s, ran a small class. He was quite famous as a logician, and he walked in the rain to teach his class, and he caught pneumonia. At the time, people thought that the cure should represent the cause for a disease. So his wife, while he was sick in the bed, threw cold water on him in order to make him better. Didn't work. And this killed him. So George Boole gave his life for education. So he is the poster child for digital design and computer engineers, and we can always thank George Boole when these things work properly. So thanks George. Very nice. So here it is, 57,005. Thank George Boole. We have a correctly defined, I think, positional notation. In any radix, this will work. So for example, if I told you that the base was going to be base 8, that we call octal, then we could say that the numbers would be 0, 1, 2, 3, 4, 5, 6, 7. That gives us a whole 8 symbols, and then we can use that number. Let's say we wanted something like, I'll give you an example, 7, well, I'll do this in octal, 4, 3, 2, base 8. How would we represent 432 base 8 in decimal? Be 4 times 8 to the 012 power plus 3 times 8 to the 01 power plus 2 times 8 to the 0 power. How's that grab you? 8 to the 2 is 64, and so 64 times 4 plus the rest. I suppose you could do the computation. So this is any base. You can use positional notation to go from what I would call any base into decimal. How about that? Good, right? Suppose you had this number which we printed, and you wanted to print it in base 16 again. Well, one thing I could do is I could call integer dot toString, and I can go toHex string, toOctal string, or toBinary string. How convenient. So integer, capital I, spelt out as a word, actually represents an instance of a class. Actually, it's not even an instance of a class, it's just a class. And the toBinary string, tohexadecimal string, toOctal string, is that a dynamic or a static method? That's static, because you didn't have to instance the integer class. So now, having done that, I can convert it to a hexadecimal string, put x in there, and expect to see something like dead come out. What do you think of that? It's dead. Right? Dead. So now, suppose you wanted to convert it to a binary string. It shouldn't be too hard. To binary string. Now I can see it in binary, and I can see it in hexadecimal. And if I can see a binary string, it should be possible for me to do binary computations down at the bit level and do all kinds of interesting masking functions and see the output. So if I wanted to, I could derive a mask, and a mask in my world is just like something that consists of a bunch of bits that you either want to turn on or off. And if I wanted to create a mask, integer, and this is very good if you're building device drivers. A lot of times electrical engineers spend time working with devices, and they want to try and make them function properly, and so they build device drivers. So let's clear the least significant 8 bits, or clear the least significant bytes, and we'll do that with a mask that says FF00. So now if I wanted to clear the mask, clear the least significant 8 bits, or clear the least significant byte, I create a new integer called, how about z? And that is equal to x and y. Now, if you notice here, I'm using a single and percent and not two and percents. A single and percent is used when you're doing a bitwise and. Two and percents are used when you're doing the logical and between two variables whose value is true or false. So that's why there are two ways to do an and they have two completely different effects. So now we're doing a bitwise and, which allows us to do 32 bitwise operations at the same time and get an output. So now when we look at the mask, and we'll make a little hex string for the mask, I should be able to also look at the output. Of the ANDing of the mask. And what do I expect to see on output? Yeah, DE00 would be the output. So now let's have a look and see what we get. I should see the binary string, hex string dead, the mask FF00, and then we see we've cleared the least significant 8 bits. Now suppose you wanted the most significant 8 bits to appear in the least significant 8-bit. That is, I want to shift DE over to the right by 8 bits. So the shift operation, that sounds like something we should be able to do. We'll give a new integer, we'll call it W, and we'll set it equal to Z, shifted to the right by 8 bits. So that is greater than. It doesn't mean it's very much greater than. It means shift to the right. And similarly, you can shift to the left. And as you shift to the right, we would expect DE to appear in the least significant 8 bits. Oops. What do you think of that? Good, right? So now DE is in the least significant 8 bits, and the least, you can see the 00s are gone. DE got shifted over. Very interesting. So now I have a question for you. If I told you that I could take the bitwise quantity x and invert it, what would that look like in binary? Well, I would expect to see all the 1s turn to 0s and all the 0s turn to 1s. And if I wanted a bitwise inversion, I could do that with a what they call a monomial operator. That is an operator that takes only a single argument, as opposed to a binomial operator like plus, which takes two arguments. So let's look at the output now of x. That is the bitwise inversion. The 1s will change to 0s, the 0s will change to 1s, and sure enough, I see it says 1101. Here it says 0010. So where this is a 1, that's a 0, but look at the least significant numbers and then compare it to the most significant numbers. These were implied 0 because they were the leading zeros. So the 11011 became 0010. So this is the part, the 16-bit part, and this is the rest of the 32-bit part. Right in here, the most significant 16 bits. What do you think of that? Good, right? So now, if I'm trying to build a device driver where I'm trying to turn on the ones and zeros and control these things, I can do that here in Java. Suppose I said to you, I'm really interested in learning how negative numbers are formulated in scalar quantities at the bitwise level. Suppose I said, okay, I'm thinking I'd like to do a computation that says 4 minus 3 equals 1. Well, I could do that, but I don't necessarily have to use the negative sign. I can say print 4 plus, and then in parentheses, tilde 3, that does a bitwise negation, plus, plus 1. Tilde 3 plus 1 is actually the way in which Java represents negative 3. And the answer is 1. So what we have done is we've represented minus as tilde 3 plus 1. Tilde 3 plus 1 negates the quantity and then adds 1. In the world of digital design, this has a name. Anybody know what the name is? What's it called? Have you not heard of 2's complement? It's 2's complement. So 2's complement, this is how computers work. I don't know if you ever believed it before because it was only shown to you by your digital design instructor and it wasn't shown to you by your computer science instructor. But as it happens, it's the way the computers work. So in fact, 2's complement is how subtraction is done inside of the computer. So if you had an instruction on an old style PDP-8 computer, which I used to program, the instruction was CIA, which stands for interesting things, but also stands for something that's computer relevant. Does anybody know? You've never seen a PDP-8, have you? Really? Never? Ah, you break my heart. Here, I'll show you the computer I used to program. PDP-8. They should have pictures, right? Yeah, there it is. Here's a picture. This is the computer I used to program. This is, you know, can we see it big? Yep, there it is. So here's the CPU. This is teletype, which uses its paper tape, which is hanging down here on the bottom as a means of physical storage. They punch little holes in the paper tape. The teletype prints at 11 characters per second, blazingly fast. These are called, oh dear, what's going on? Stop it. There's an advertisement. I can't make it go away. This is terrible. It's selling me diapers. How do they know I need them? So as it happens, if you can get beyond the screaming baby with the diaper issues, you can see the computer. And I'm going to be on travel. I mentioned this to you before, right? I'm cursed. I have the travel curse. Whenever I travel, they always seat me next to the screaming baby with the diaper issues. And that's what this is reminding me of. It's not for very long. It's only 7 hours. And you can't move because you have to keep your seatbelt fastened while they're screaming. I'm bringing earplugs, but I think I should also bring nose plugs. So you have the blinky lights on the front, and then there are these buttons in here on the bottom for encoding the binary, and they group them in 3 buttons at a time because it's in octal. and this is a very peculiar thing, the PDP-8 is a 12-bit machine. At the time, people didn't think 8 bits was enough, but they didn't have enough budget for 16 bits, so they compromised and made a 12-bit machine. So what does CIA stand for? This is a standard PDP-8 instruction built into the computer hardware. Nobody knows, huh? It's complement and increment the accumulator. So complement means takes the ones and turns them to zeros, takes the zeros, turns them to 1, and then adds 1. And they do that in preparation of a subtraction. And they do the subtraction by addition. So once you have done the underlying bitwise manipulations to create the 2's complement, all you have to do is add the numbers together and you're subtracting. Pretty slick, right? This works with anything. So if we put in 27 and then the number in here is 30, we would expect the output to be 3. Eventually. What do you think of that? 2's complement. Bet you never thought you'd see that again. Well, there it is. There's a 3. So now we've seen bitwise manipulations in Java. We can do negation. We can do ANDing. What about OR? Right? You've got 3 basic operations which allow us to express all possible combinational logic. AND, OR, and NOT. And with this, we can derive all Boolean algebraic expressions. Oh dear. Just a minute. The computer says that the phone is either on or it's off. I'm a computer engineer. Everything should be on or off. And that's it. So as it happens, by the way, you can't do this with an iPhone. At least not easily. So suppose you wanted to do something with the OR operation. Let's see now. We've got z equals x ANDed with y. What would we get if we came up with a new variable, x, y, z, w? How about h equals x, and now there's a kind of OR called an inclusive OR. So there's 2 kinds of ORs. One is called inclusive OR, the other is called exclusive OR. And for the inclusive OR, it's x single bar y. Have you heard the term inclusive OR? It's the OR you know. Right? So if anything ORed with 1 is going to be 1, that is, 1 OR with 1 is equal to 1, 1 OR with 0 is equal to 1, then if FF is all 1s, 8 1s, then what would you expect to see in the most significant byte for H? 1, right? It would be FF. So when we print out H at the end, I would expect it to see FF and then the least significant 8 bits, which is AD. Oh, you're late. Oh, I forgot to put it into hexadecimal. Integer dot to hex string, and there you go. Is there a question? So there is FF in the most significant byte, AD in the least significant byte, and so now what we've done is we've set all the bits in the most significant byte of the input word. What do you think of that? So now we've done and, or, and not. And with these things, we have completeness in terms of Boolean algebra. What do you think of that? Good, right? Now, how about another kind of OR? The exclusive OR, right? So now, if you said exclusive OR, what we could do is we could create a new variable, integer, how about g, is equal to y exclusive OR with y. So now up arrow is being used for exclusive OR. Single bar is being used for inclusive OR. Exclusive OR you know already because 0 exclusive OR with 0 is 0. 1 exclusive OR with 0 is equal to 1. 0 exclusive OR with 1 is equal to 1. And 1 exclusive OR with 1 is equal to 0. Quite right. So if I take y and exclusive OR it with itself, what will the output be, do you think? I know, it'll say arithmetic exception at runtime, right? No, it's a legitimate computation. It will give you a correct output. The output will be 0. Because anything exclusive ORed with itself is always 0. So when we write out G, we would expect it to say G equals 0. That's what a bitwise exclusive OR operation does. G equals 0. What do you think of that? Good, right? So now I've got all the operations. And, or, not, exclusive OR, and we've covered 2's complement. I hear a lot of murmuring in the background. Is there questions? No questions? I hear the murmuring because someone has a question, I think, but maybe not. I don't know. So then I thought, well, all right, this is terrific. I feel like I've got a good handle on all the operations, and now I think maybe I should be able to use these operations in order to input and output a wide variety of different truth tables. What if I wanted to generate all the possible inputs for let's say, is there a question? You guys keep chit-chatting. I think it's going to be distracting this way. Suppose I wanted to create all possible inputs in a truth table. Let's say I had, I don't know, make up a number, a 3-bit truth table. How could I generate all possible inputs? Right? It's 0, 0, 0, 0, 0, 1, 0, 1, 2. What am I doing? I'm adding 1 to the prior number to get a next number, which is also called counting. Right? I'm counting. So if I want the computer to be counting for me, I can write a little bit of a loop. Right? Maybe a for loop is a good way to go. So let's do that. We'll write a little for loop. We'll count to 7. For integer, have we used I yet? Equals 0 while I is less than 8, I plus plus. Oops. And then we'll print out I in binary. And then integer dot to binary string. And we'll put in I. And I think maybe you're ready to see the wondrousness that is the input for some truth table. Maybe. Yep, there it is. 0, 1, 1, 0, 1, 1, 1, 0, 0. It's all working. How about that? So now suppose you said, well, gee, I don't want it to just say 1, 0, 0, 0. I want it to say true, false, false. I want it to actually print these numbers. If the quantity in the least significant bit is going to be equal to a 0, then I will use a quantity with a string called false. If the quantity in the least significant bit is a 1, I will output a true. So what I'd like to do is I'd like to print out the bit string without a carriage return. So I'll remove the print line and just make it print. And then immediately afterwards, I would like to put in sout control J enter, quote space, and now I'd like to define something that will output true or false if the least significant bit is equal to 1 or 0. How could I do that? How can I test the least significant bit? Well, maybe I need an if statement, huh? How about this? If. Now, how will I identify the least significant bit? It's I, right? I want the least significant bit, so I need a mask. So here comes the mask that we talked about before, 0x1. Right? So the least significant bit is I ANDed with 0x1, and then check it to see if it's equal to 1. And we need parentheses. And so then if it's equal to 1, we can create some sort of a flag, a Boolean flag, and set it equal to false. And then if I have a 1 in the least significant bit, what I can do is I can set the flag equal to true. Otherwise it remains false. And so now I can put out the flag. What do you think of that? So my least significant bit mask is being ANDed with the variable I so that I can isolate that least significant bit and then check it to see if it's a 1 or a 0. This is essentially checking to see if it's even or odd. And now what we'll do is run the function, and we would expect this to output an alternation of false and true. Because 0, yep, there it is false. 1 is true. This is false. That's true. False, true, false, true. Sort of working, right? More or less. So now let's assume that when it's 1, 1, 1, it should say true, true, true. But if it's 1, 1, 0, it should say true, true, false. Right? So in other words, I'd like to do this for 3 bits. We already know something about the shift operations. So what I could do is I could create a, I'll call it a dummy variable. And for the dummy variable, I'll use the second digit, and I'll call it integer J equals I shifted to the 1, and maybe we could AND it with, well, we'll do this in one, oh, I see, I got it wrong. I was staring at it blindly and going, why isn't it shifting? So there's J. So now what do I do? You tell me. Right? J represents the next digit over. So that's being shifted. Shifted over to the right by 1. I'm still trying to identify whether that bit is going to be a 1 or a 0. So what I'd like to do is I'd like to create an AND operation. With 0x01. What do you think of that? And now, if it's a 1, J becomes a way in which we can set the flag to true, and otherwise it would remain false. So what are we looking at? If this flag is equal to the flag of the 0th digit, we need another flag. This is going to be the next digit over. So here's another Boolean. We'll call it flag 1, and we'll set it equal to false. And now if J is equal to 1, then we'll set the flag 1 to equal to true. So what have I done? I've isolated the least significant bit, identified whether it's a 0 or 1, mapped it to a Boolean operation that allows me to set something to be either true or false. Then I took the second least significant bit and then proceeded to isolate that, and then mapped it into a flag which allows me to output true or false. And now when I output these flags, I could say plus flag 1 plus quote space quote plus, and now I got the 0th flag. There's 2 pluses. That's bad, but the other one is good. So let's see if that works okay. So it should give me the least significant bits as being true or false, in theory. So let's see. It says 1 0 is true false, 1 1 is true true. So it's working. Right? I'm getting a truth table with Boolean operation outputs. So now you've seen me do this twice. What do I do for the third bit? Right? For the first bit, we shifted over by 1 and then ANDed with 1. For the next bit, what do we do? Really? I have to shift over by 2 for the next bit. This gives me K. And now I've got another flag, Boolean flag two, and that should be equal to false. And now if K is equal to 1, I can set flag 2 equal to true. What now? You tell me. I want to print the value of flag 2, right? I didn't get that far yet. You guys are not allowed to just sit like lumps on bumps. You have to help. So plus flag 2 plus quote space quote. And now I've got the 3 bits being mapped into 3 symbols. Each one of the symbols will be true or false respectively. You don't need object orientation for this, right? But at some level, what we've done here is we've mapped the bitwise Boolean operations into logical Boolean operations. And now we can proceed to output our truth table using true and false or using 1 and 0. We can do either. What do you think of that? Good, right? So suppose the input variables are numbered A, B, C. And then you can say A, B, C will iterate through all possible values, giving you a 7-entry truth table starting at number 0 and iterating out to number 7. So if you have these Boolean algebraic values, right? So I can basically say flag 1, flag 2, and flag are A, B, and C. So if I said that is the case, let's refactor the expression. And by refactor, what I mean to say is that flag 2 will be the A variable, and I will hit Shift F6 and make this variable A. Whoops, he's giving me a hard time about it. A. Then I'll go to flag 1, hit Shift F6. Oh, flag 2 is not finished. Okay, now it's finished. I hit Escape. Shift F6, and we'll make this a B. Enter. And now we'll get to the next flag, Shift F6, and we'll make that a C. A, B, C. So now, if I said to you I wanted to find A and B and C as the output function, I could write A. Now it's not bitwise AND, it's logical AND. So it's not a single ampersand, it's 2 ampersands. A and B and C. And it's not working. Did I do something wrong? Maybe I need to group it with parentheses. Oh, yep, he's good with that. So what have I done now? I've taken the logical and operated on 3 logical variables, A, B, and C. These variables have been extracted from the binary vector which was encoded into the integer by virtue of shifting and masking. That's how you do these extractions. Now we should be able to iterate through all possible values of A, B, and C and see the outputs when they get ANDed together. In other words, we've encoded a truth table. And the only time it's true is when all 3 are true, 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 ANDed together, and the output is true. That's pretty good. So now, if you wanted to, you could make it look nice. How do you do that? Well, I don't know. Probably put in a print statement or something. And then you write, quote, A. I'm liking tab, but I don't know if that'll work. B, C, and then he's giving me a hard time. \T should give me a, oh, I see, there's a \C in here. Yep, that's his problem. And now we wanted to say equals, and now it's going to be A and B and C. So \t gives me a tab which will space out A, B, and C somewhat. I hope. Yeah, it does space it out somewhat, but it's not quite aligned, but that's all right. I'm okay with that. So what if I wanted to do another function? How about another function? We'll do the same thing as before, only with a difference. And the difference is we'll use OR. That's a good one. Inclusive OR. So A, 2 vertical bars, B, 2 vertical bars, C. Let's get rid of this nonsense here. And so now we'll have A or B or C. So I think it will always be true except for the first one, which is all zeros. And that is true. So now I've got a way to express truth tables for 3 bits, and I have a way to generate all possible input values and then do the extraction of the outputs. What do you think of that? Now what would have happened if I said, gee, I don't want to do it for 3 bits? If I wanted to do it for 4 bits? How much more work would it be to do it for 4 bits? Well, given the way I've done it here, maybe double work, right? Because you're going from 8 different auxiliary variables, or three auxiliary variables to perhaps, yeah, you're going to need well, another auxiliary variable. It's not too bad. You'd have to add a D in there. But that's not, yeah, that's okay. I think in the homework you need to do it for a 4-variable truth table. So that's, that's a little extra work. What do you think of that? Good, right? So this is like one of the homework assignments out of the back of chapter 3. That's kind of why I'm going over it now. Yeah, in the back of chapter 3, if you look at the truth table, it says A, B, C, D. So there's an extra variable involved, which I think is very useful for you guys to derive on your own, because you can feel tired from watching me do these exercises, but unless you do the exercises yourself, you will not get the benefit. So it's kind of like sit-ups. You can watch me do the sit-ups, but you're not going to help. It's not going to help you. You have to do them yourself. So we'll get you to do the next variable for the homework. I'm listening to this murmur, and I'm thinking there's questions. Other questions? No questions? So I've got a x and y, or x and y prime. How would I form the negation? Well, let's see now. Suppose I said to you I wanted NAND instead of AND. How could I do that? Well, I suppose I could put the bang in front of it, and that will invert all of the trues to falses and all the falses to true, and then this will create a NAND gate, a 3-input NAND gate. You guys know NAND means not AND, right? At digital design. However long ago, I don't know, you probably forgot because it was a while. But now you can see that this is no longer an AND function, it's a NAND function. So everywhere it was true is now false, everywhere it is false is now okay. You're killing me up here. All right. So if you wanted to be able to formulate bitwise negation, you use the little tilde. If you want to form a Boolean negation, you use the exclamation point. Both the tilde and the exclamation point are monomial operators because they take only a single argument, as opposed to the AND operation, which is a binomial operator because it takes two variables on input, just like OR and addition and subtraction, all binary operators, binomial operators. So, what do you think? You guys are now expert, right? Expert. Why do I care about all of this bit flipping? What possible difference could it make? Does anybody actually do this kind of bit flipping? The answer is yes, they do. Yes, they do. For example, if you have a pixel, I'll just make up a pixel. Pixels are encoded with red, green, and blue colors, typically. So the integer red could be equal to 255. The integer green would be equal to 255. The integer blue could be equal to 255. And for some reason he's pretty unhappy because I've already used up green and blue. I should probably start a separate example. Let's do that. So we'll do a new one. We'll call it the color pixel example. And in this one what we'll do is we'll have a little main method which has red, green, and blue. If red, green, and blue have equal components, then the color is said to be gray. If they're maximal, that is to say 255 is maximum and 0 is minimal, then each one of the colors is said to be white, equal quantities of red, green, and blue. So now, if you wanted to create the pixel, what you would do is you would say that red is in the most significant point, green is in the next significant byte, and then blue is in the least significant byte. So to create your pixel, integer I is a pixel. Let's call it P for pixel. Set it equal to R plus G plus B. But the G has to be shifted over by 8 bits, and the R has to be shifted over by 16 bits. In doing that, what you have done is you have packed the pixel into a 32-bit quantity. This is very common if you take an image from the screen or from wherever and you want to decode it in Java into red, green, and blue color planes in order to do operations. So as a result of this, you will also find that there is an overlay plane which some people call alpha, but which I will simply call A. And I will set that to 255 as well. And in the alpha plane or overlay plane, I will shift over by 24 bits. And now I have successfully packed a pixel into a 32-bit quantity. This is so compelling for me as a Java virtual machine programmer because the Java virtual machine is native a 32-bit machine. So Java virtual machines underneath have a what's called RISC or reduced instruction set computer model based on 32-bit quantities. So until you hit the just-in-time compiler, everything looks like it's 32-bit to Java. So packing into a 32-bit quantity is a very efficient way to go. It's also the default representation for almost all direct color images. And so this enables us to do all kinds of interesting and wonderful image processing. And now I'd like to take a little survey from the audience. Who here prefers day classes? Only a few? Oh, a lot. Everybody. Almost everybody. Who here prefers evening classes? Late at night, starting at 6:30 and ending at 9. You like that better? Really? Is it because you work during the day? No, you just stay up late. Why would you like it better? You like evening better? I can schedule either way. Day classes are better, aren't they? I'll tell you what happens with the evening class. You end up walking around in Bridgeport in the dark. You like to walk? It's adventuresome. As it happens, I used to work in Bridgeport, and it's a tough town. So if you're ever tempted to walk around by yourself in the dark, don't do it. It's bad, very dangerous. So I like the idea of moving to day classes if we can, but it sounds like some people prefer evening classes.
No.
Show of hands again. Who prefers the evening classes? Not so many. Oh, okay. You didn't like my story about Bridgeport. Okay. When I worked in Bridgeport, and I'm recording this, so I have to be careful, I never stopped at a red light. The police would pull me over, and I would say, my colleagues tell me it's not safe to stop. These colleagues? Oh, yeah, I'm a professor. And oh, yeah, you can go. Don't stop. Go. Because you're a target when you stop at the red light. That's assuming you're driving. If you're walking, you're a target no matter what. So this is a this is my encode the pixel example. Can you tell me, please, how would you decode the pixel to get red, green, and blue back? You don't believe me about the Bridgeport? It's true story. It's true story. By 6:30, you could hear gunshots. Yeah, it's not safe. I sent email to Chris Johnson, to try and get him to put a shuttle in for weekends and also for the evening classes. They're still having a discussion about it. Chit-chat, chit-chat. Send him email. Let him know you need these things. It's very important. So now let's assume you would like to extract the least significant 8 bits. So I want B to be equal to something which will allow me to extract the 8 bits that I put in there to begin with for the encoding. So I start with the pixel, and then I AND it with 0xFF, and it gives me a hard time. Oh, it's not AND, it has to be single ampersand. Bitwise AND. I was using ampersand because that's Boolean and I was just doing it. But if you're going to do bitwise extraction, you've got to use a single ampersand. Now suppose you wanted to extract the green quantity. What would you do? Green equals P. Oh, you say and. And then what? It's 8 bits been shifted over, so you got to shift it back. So shift it first. Shift it back by 8 bits. Then, after that's done, AND it with 0xFF. So you see what's happened? I took the 8 bits and shifted it so that it's the least significant 8 bits. Then I used my mask to extract it, and then I did my set. You see? So suppose now I want red. I must shift by how much? 16, right, the same amount I shifted to the left. Now I got to shift to the right by 16. I proceed to AND it with 0xFF. And suppose I want alpha. Same thing, I shift to the right by the same amount that I shifted to the left, 24, and then I do my AND. And that's it. So now you've learned how to encode and decode a 32-bit packed quantity called a direct color 24-bit pixel with overlay plane. And that's how we do it, folks. Real computers work this way too. So if you're ever thinking about doing some image processing, this is what's going on underneath the hood. What do you think of that? I've wrapped up chapter 3 now, and I'm ready to move on to chapter 4, but I would rather have questions from you. Am I going too fast? No? Am I going too slow? Okay. I can go faster. So let's look at this next chapter, chapter 4. Chapter 4 is on base conversion, and we talked a little bit about that at the beginning of the class. We started to do radix conversion. We went from base 16 to base 10. To do that, we used positional notation. In fact, if you wanted to go from any base to base 10, you could use positional notation for that. Has everybody seen this before in their digital design class undergraduate? Yeah, I think so. So radix conversion, that's not too difficult. I think you guys probably know this stuff already. But I'm not entirely sure you know it. I could give you a little quiz. Let's see. Okay. Let's set this number to 0x17. Now, let's take red and print it. S out, Control J, enter. Integer dot toString. Only this time what we'll do is we'll put in red and the base that we're interested in, 16. We can make the base explicit, which means you can try and use interesting bases like base 15 or base 13, bases that you wouldn't otherwise normally use. I expect it to say, it says 0. Did I make a mistake? I'm going to print before and after the encoding and the decoding, because it seems like I've got a mistake somewhere. Copy. Paste. Where is my mistake, I wonder? Oh, it's working. You know what it was is the order of precedence. The shift operations had to happen first. So the encode and decode are working, I think. Let's see what else we need to know about this. I think we can put this chapter to bed. I'm doing it all without PowerPoints, by the way. I have PowerPoints for each chapter, but I'm not doing PowerPoints because power corrupts, and PowerPoints corrupt absolutely. So I'm thinking we've got the base conversion down. I will I'm going to move on to control structures, unless you guys want me to dwell some more on base conversion. More base conversion? No. Okay, it's time to move on. So suppose we did something that you might not be familiar with. Let's try the following. Let's try the switch statement. Here's the switch statement. The switch statement says that it will do what I call a computed goto. A computed goto is much better, it's much faster than if then else. For example, if somebody said if C is equal to left parenthesis, then do the left parenthesis thing. If C is equal to left bracket, then do the left bracket thing, that long dispatch would take on average order n on 2, where n is the number of dispatch tests, time in order to do a computation. But if you do this with a switch statement, the switch statement will execute in constant time. The reason why is because the scalar input, which is used, creates a table. And for any given quantity that's being used, you map straight into the table, which causes a non-local transfer of control. That is a jump of the CPU. That jump table comes from this pre-computed mapping that's done inside the compiler. So any compiler worth its salt is going to do a switch statement in constant time. But here's the limiting factor. The switch statement must use a scalar input. That means it can be a byte, it can be a short, it can be a char, it can be an int. It cannot be a long, it cannot be a float, it can't be a double, it can't be a string. So as a result of this, you are somewhat limited when you use the switch statement. Somewhat limited. Let's start a new example and we'll do a little test. So, hello, switch. Oops, S-W-I-T-C-H. Okay. So we'll put in a little PSVM, Control J, Enter, a main. I'll put in my little character. So here's my Unicode character, char C equals single quote left parenthesis, end quote, semicolon. And then for my print statement, I would like to have a way to conveniently print. So I'm going to define my own print statement, public static void print, which takes a string, S, and then takes S and runs it into system.out.println. Why do you suppose he's giving me a hard time about that? Oh, because it says print line instead of print. There you go. Is it warm in here? I think so. Yeah, it won't listen to me. So I have this idea that I should be able to extract characters from a string. Let's create a string. String s equals end quote hello world of parentheses, end quote sem. So now I have a reference data type, and it's called a string. It's different from the char because the string is going to give me something that is like a pointer in C, but in fact we call it a reference in Java. And the char C will be passed by value, but the string S will be passed by name or reference. And I would like to be able to convert the string S into an array of char. Right? That sounds reasonable, right? Because if you think about it, a string is very close to an array of char. So what I'll do is I'll create a new array called char array CA, and I'll set it equal to s dot to char array. So that's cool, because now that means I can use a for loop, and I can iterate through each one of the elements inside of my char array. So let's do that. For integer equals 0, while integer I equals 0 while I is less than ca.length, a built-in tag for determining the length of the array. In C, you have a trailer, you keep going until you get to like -1. But with Java, you know the length of the array already. And just like C, Java starts numbering its arrays at 0. So now you could say I++, and just for a good time, what I'll do is I'll print out the value of CA of I. So this will let me print out the array. And it'll say something like hello world parenthesis whatever, and it'll do it in a straight line down the screen, I think. Yeah. So now for each one of the elements in my array, I can do some processing. This is a very cumbersome looking switch statement, and it's cluttering up my main method. So what I would like to do is refactor the code and extract this list of statements into a single static method. It'll be my character processor. So what I'll do is I'll go to my refactor menu and extract a method and give it a name and call it something like char processor. So now the char processor looks like it could take an argument. Maybe that argument should be a char called C. And now CA of I will resolve itself to a Unicode character. Unicode, by the way, is the 16-bit term used for characters in Java. Java does not use ASCII like C does. Java uses 16-bit quantities because you need 2 to the 16 different possible symbols if you want to start to internationalize your code. That is, if you want to use all the different ideographics in kanji, you need lots and lots of characters because they're using, in an ideographic language, they use one symbol to represent something like a word. So if you wanted to trace kanji back, you would see a turtle kind of looked like a turtle, and eventually over the eons it evolved to a more modern kanji character. So if you wanted to try and do Japanese, you'd need lots of characters. That's why they use this Unicode. So now for each character in my string, I can do my little character processor. And if I wanted to say that an H came in, I could devise a case statement with an H in it, and then I could say the character is H. So here's the H, then a series of unknown symbols, and then the left parenthesis and the left bracket. So let's take a look at this. The switch statement takes a scalar on input, but it can't be a long. The case works with a series of different values which have to be of the same general type as what you're switching against. What about those break statements? What does break do?
Program stops execution.
Yeah, it stops the flow of control so it doesn't proceed to execute the following case statements. And then the default will only execute if none of the other things execute prior. So break does a non-local flow of control change to the containing scope. So if the containing scope is from here to here, break will break you out of that containing scope. What do you think of that? Now, what would happen if you wanted to look at the broken for loop? So let's do the broken for loop. I like this because we're going to break a for loop with lots of break statements. So what we'll have here is a doubly nested for loop. And we'll do it with an array. And we'll have it like this. Public static void main control J enter. We'll do a two-dimensional array of int. Integer array, 2 dimensions, equals, and then we'll say new int of, let's make an array that is 3 by 3. Certainly if I can do a 3 by 3, then later I could do 30 by 30 if I like. Then what we'll do is we'll write a doubly nested for loop that will create the identity matrix. The identity matrix is defined as being all 0 except when the row number and the column number are equal. So what we'll do is we'll write a doubly nested for loop to iterate through all row and column numbers, and then we'll check for equality. So let's start by iterating with the rows first. For integer r equals 0, while r is less than, now here's the cool part. If you want the rows to be in the first bracket, use a dot length, and that'll tell you how many rows there are total, and then say r plus plus. And then if you wanted to iterate through the columns, say for integer c equals 0 while c is less than a of 0 dot length. For a matrix, all the columns should be the same. Oops, I'm having a trackpad issue here. And then say plus, sorry, semicolon c plus plus. Okay, if r equals c, then a of r, oops, he's doing it again. I hate this trackpad. A of r c equals 1. So that will allow me to extract a 3 by 3 identity matrix. What do you think of that? Good, right? That's easy. So now suppose I wanted to go through the identity matrix and print it. Instead of an if statement in here, we'll do the print statement separately. We'll say something like this. S out, Control J, enter. Actually, I don't think you want a print line. You just want to print. A of R C, so that's row and column. And then after you print out all of the elements in the column, you put out a blank line, and then you proceed to continue. So for the purpose of iteration, we're able to obtain a doubly nested for loop which can now manipulate two-dimensional arrays. There's some chit-chat in the back. I'm thinking there are questions. Are there questions? So here's my little identity matrix printed for your enjoyment. Right? So I can divide this now into small little modules. The first one is here, which will allow me to, I'll refactor it and extract it to print a matrix. Print a matrix is something that seems generally useful. I'll call it print. Okay. So now you can sort of see this will print an arbitrary matrix A, as long as it's square and integer. And this over here is also interesting, I think. This allows me to get an identity. I'll refactor that. It's generally a nice tool. So I'll turn it into a method and I'll say get identity matrix. So now we have A and we have the identity matrix. What if you wanted to get the identity matrix of any size? So I could make the size an integer, and we can put the size in here. We assume the number of rows and the number of columns are equal because it's a matrix. And then what we'll do is we'll pass in a number like 3, and now when we run this, it gets me an identity matrix and then prints it out nicely for me. So if somebody said, well, gee, what would happen if I wanted a, I don't know, make up a number, a 6 by 6 instead of a 3 by 3? It should do it without error, in theory, and certainly it will do that. So you can make arbitrarily sized matrices provided you have sufficient memory. And I think we have quite enough for our little examples here. But I promised to do the broken for loop, right? The broken for loop. So what would be a way to break out of this for loop? Well, if you discovered that R is equal to C, do you have to keep going through the rest of the columns? No, because it only happens once in any given row. So then you can break. And that will allow you to say, hey, I'm done with this row. Let's go to the next row. And in theory, it should work, because it will break to the containing for loop. It won't break out. So it continues to work, but it does less work. That is, it becomes more efficient and runs faster, because after you're done with that row, you can break out to the containing for loop. But as it happens, you can also create labels. Here's a label called label 1. Well, now it's called label 1. Now if you wanted to break, you could break to label 1. And now your broken for loop is really broken, because as soon as it encounters a 1, it will stop. And it will not do any more. And so you'll just see a 1 in the upper left corner, and that's it. In other words, it's broken. So instead of creating the identity matrix, what it did was it said, aha, I found a 1, I'm done. And it broke out to the outermost loop, because you identified that loop for the inside for loop. And so it gave you a non-local change of control to that outermost loop. You know, they say that Java doesn't have go-tos, but it does have labels, and you can break to those labels. So is it a go-to? Not really. It's still structured programming, but it's getting pretty close to a go-to. And this can, when abused, be a fruitful source of bugs. But it's part of the language, and we have to deal with it. How am I doing on time here? Oh, we're almost done. Let's see if there's any other goody things. Have you seen the label thing before with the breaks? That's new, right? That's somewhat new. For loops you've seen, I'm sure. But the labels with the break, that's a little bit exotic. And I think in terms of the switch statement, it's probably the most advanced topic, that with the break statement. The only other thing that I would do that's a little bit different is I would point out the getting of the identity matrix. When you get the identity matrix, how do you get it back? And the answer is you do a return. That return can appear anywhere inside of your code. So it's another way you can do a sudden change in control. A lot of times if you have multiple returns inside of your code, they don't feel like it's structured, but Java permits it. So if you wanted to, instead of breaking at this label, you could just say return A. Now he's not liking that. Oh, because it says break return. There. So now the first time it encounters a 1, it will just return A, and so it'll do essentially the same thing as the break to the outermost label, giving you a 1, and all the rest will be 0. So the return is a sudden change in control. It interrupts the flow of control of the program. So you can put the returns anywhere you like in Java. A lot of people in a software shop will say that's not a nice way to program and you shouldn't do it, because it doesn't give us a clean way to refactor or to do the analysis. So here's what you can return. You can return any quantity that's been called by value. You can return any quantity that's been called by name. So you can return instances of classes, you can return integers, you can return bytes, you can return arrays, you can return reference data types, whatever you like. Return will return it. Now, somebody might say, "Oh, Professor Lyon, how wonderful this is. You should have some sort of a library for doing matrix arithmetic." As a matter of fact, if you take a whole series of different operations for a class of problems that you're trying to solve and put them into a single class, that is called a toolkit. And I have created some toolkits which are available for you. So for no particular reason other than I think it would be good to explore that a little bit, I can show you that in the math package there is a whole bunch of stuff which allows you to do these kinds of things. So for example, here's a Mat1 class or Mat1 toolkit which allows you to do a whole bunch of one-dimensional matrix manipulations. If you go into IntelliJ and show the members, then you get a plus sign on the left. If you click on the plus sign, it allows you to see all the different operations which are available to you. And so doing things like computing coefficients of variation, doing dot products, doing Brownian motion, doing summations, getting statistical quantities, all of that's available to you in the one-dimensional package. Finding outliers, doing thresholds, building windows, things like that. Then there's a two-dimensional package which has a perhaps comparable number of functions for doing two-dimensional operations efficiently. So when you're thinking about doing something like a matrix multiplication, it should be optimized here. And if it's not, well, blame me. I try to optimize it. It may not be. There's an inverse function. I would have hoped there would have been an inverse function. Get the inverse, huh? He's not doing it. Oh, here's three-dimensional arrays. Let's see if that works. Multiply. There you go. So instead of using for loops, the multiply is written out. Let's see if we've got some. Here's the invert. Here's a fast way to do an inversion. Normally, if you do the inverse of a matrix, it's the transpose of the adjuncts divided by the transpose of the cofactors divided by the determinant, which are the adjuncts in the matrix. But this allows you to do it in one swell swoop by creating a series of auxiliary variables. So this is done with a symbolic manipulator that allows you to output these things without for loops. So for 3x3 matrices and for 4x4 matrices, I've special cased them because they happen so much in computer graphics that I wanted them to be very efficient at finding inverts for the inverse of a matrix. So we've got what I would call toolkits. They represent frameworks for doing certain kinds of things. doing it general for arbitrary sized matrices is a little bit more difficult. See, if the invert is shown here, you can see it. As you proceeded to do the inverse for this matrix, things get a little bit sticky because you've got a lot of equations. And you can see how that tends to explode when you go to, let's say, a 5 by 5 or a 6 by 6. Thankfully, I don't need those things very often. The 4 by 4 has a good role for what I call homogeneous coordinate transforms. So that's a thing that they use in computer graphics, in 3D. And when you look at this return, you can see he's creating new matrices, 4 by 4 matrices, from the auxiliary variables that were devised in the code above. So these things are available to you in the code for the course, should you need them, although I don't expect that you would. So we've seen some interesting things going on today. We did let's do a little review. We did the operations. Binary operations can be done at the bitwise level, and they can be done with Boolean. So the Boolean operations, if you want to do an AND, that's 2 ampersands. If you want to do bitwise binary operations, it's a single ampersand. If you want to do an inclusive OR with Boolean variables, that's 2 vertical bars. If you want to do a bitwise inclusive OR, it's a single vertical bar. If you want to do an invert operation bitwise on a scalar, that's using a tilde. If you want to do it with a Boolean operation, you use an exclamation point. If you want to use an exclusive OR, can anyone remember exclusive OR? How do you do exclusive OR bitwise? Up arrow, right? Up arrow. How do you do an exclusive OR with Boolean operations? How do you do it? It's a trick question. You can't do it. Java doesn't have it. So there is no exclusive OR operation for logical operators, only for bitwise operators. How's that? Trick question. Sneaky! So there you have it. You can't do an exclusive. Why? Why can't you do an exclusive with Boolean variables? I mean, you could do it bitwise. Why not Boolean? Why? Why? No? Any ideas? I always ask. Nobody knows. I don't know. I have no idea. This is just the way it is. You know, they could have put it in there. They built the language from scratch. I mean, this is a new language. They could have put that in there. They didn't put it in. I don't know why. You have to formulate it by hand, right? I mean, this is sort of a weirdo thing. I guess it's just, I'll say, I cannot defend the design choices of the language. I can only present the language as it is. They haven't really talked a lot about the history of Java and its design. The only person who really talks a lot about the history of his language is Barnes Straussup, and he talks about C++. And he talks about its history and his history. But I never hear Guy Story, who's one of the progenitors, or James Gosling, talk about why they made certain language choices for Java. I don't know why they did these things. Maybe someone here who's interested could find out and tell us. But for some reason, there's no exclusive OR for the Boolean operators. Why? I don't know. So there it is. The base conversion, we talked about that a little bit. And the control structures, I think we went over that sufficiently so that you guys are pretty much into it. Here's a string switch. Pi. Here's pi. How does this work? Oh no, it's using big decimals. Does this work? Let's just do it anyway. You know that in Java, the precision is limited by the underlying primitive data types, such as integer and short and long and byte and double and float. But if you are unhappy with the number of digits of precision, Java has an answer for you, and it's called big decimal. And big decimal packages allow you to do things like this, computing pi to many digits. And so if you're interested in doing that sort of thing, here's the big decimal thing. Here he's got four digits, big decimal constants using pi. You can set the number of digits in big decimal to anything you like. Covering this now doesn't make sense because we're running out of time, and it also isn't something that you have to care that much about. But you can do, here's the arctangent computation we saw from before, only done with big decimal. And if you can get arctangent to be computed with lots of precision, you can find that as a convenient way to compute pi. There's some formulas for this. So this gives you a way to program the precision to anything you like. I won't belabor it too much, but I just wondered why we wouldn't get more than, I don't think I saw 10,000 digits here, but maybe it stops it after a certain amount of time. Oh, wait a minute. Oh no, it goes on and on and on. Yeah, that could be 10,000 digits. Good, good. So that's that's kind of an interesting thing that you can do if you feel like you need to sit around and compute pi all day. Do people do that? I think they might. You might need it, right? Because if you're in a spaceship and you're going to another galaxy, and then there's all these orbital mechanic things, and you'll be happy you can compute pi. There must be other reasons people need so many digits of pi. I can't think of them offhand. But orbital mechanics, that's a good one. My boss at Jet Propulsion Lab, that's all he did. He was orbital mechanicist. Carl. I just remembered his name. Can't remember his last name. Salloway. Carl Salloway. All he did was orbital mechanics. He must be retired now. He was an old fella. So there it is. That's what I have for today. I think we did enough for one day, and it's 4 o'clock. So it must be done. If you have still questions about your computer or about IntelliJ, or you need some help with something or other, please stay, and I will stay with you, and we'll work out the problems together. Thanks very much. Have a good evening.